In this episode, we will construct a parallel LCR circuit where a resistor is in series with the voltage source and one inductor, one capacitor and one resistor is in parallel with the same voltage source. We will apply PWL source and transient analysis to observe the time domain response of the circuit. Next, we will apply AC input voltage whose frequency we will vary over a long range to observe the frequency domain response of the circuit. So, stay tuned, stay focused.
Hey guys, welcome back. In today's episode, we will construct the LCR parallel circuit, and here we will apply the resistance in series with the input voltage and one inductor, one capacitor and one resistor in the parallel connection with the input voltage source. Now for this particular circuit, we will apply two kind of analysis. One is a time domain analysis, another is the frequency domain analysis. The time domain analysis will be done by the transient response, and the frequency domain analysis will be done by the AC response. That is AC analysis, and the transient response is done by transient analysis. Before going to the circuit construction, I would like to mention that I will be using the keyboard shortcuts, and you are already familiar with the keyboard shortcuts. So let me start constructing the circuit. For that, I'll go and double click the LTSpice icon, and here you can see the LTSpice window has opened. Now here I'll go and click the new schematic or the new file icon here, and the blank dashboard opens for circuit construction. I'll save this particular file. I'll go to file, then save as, and I'll give the name LCR parallel circuit 2, and I'll click save. You can see that the name of the file is appearing at the topmost corner of the left here. So I'll be start constructing the circuit. For that, I'll first hit the V in the keyboard to bring the voltage source. I'll put it here, right click to vanish it. Then I'll hit R from the keyboard. I'll click Ctrl R to rotate the resistance, and I'll click it here. Now I'll right click to vanish it. From the keyboard, I'll hit L for the inductor. I'll place it here. I right click to vanish it. Then I'll hit C from the keyboard. For the capacitor, I'll click to place it, and I'll right click to vanish it, and then again I'll hit R from the keyboard and I will click here to place it. I'll right click to vanish it. Now all the basic components are done. I will do the wiring. For that, I'll hit W from the keyboard. I'll click here, go up, go right, click here. Then I'll click here, go right, come down here and connect. And I'll connect here, come down, go right and go up and connect. So at this corners, I am just doing a one click to mark there, and then I am coming down. Now I'll click here, go up and click here. I'll click here, come down and click here. Similarly, I'll connect this capacitor also. So the circuit construction is done. I'll right click to vanish the wiring, and I'll save the file. One thing is remaining, the ground line is constructed. However, the physical ground has to be added in the circuit. For that, I'll hit G from the keyboard and I'll click here to place it. I'll right click to vanish it. I'll hit W to wire this ground to the ground line. I'll right click to vanish it. Now I'll go ahead and save the file. You can see all the circuit components placeholders are there. For the transient response, I have to configure the voltage. So I'll right click here, go to advanced, and then I'll go to the PWL. And here I will give the values. We have discussed about the PWL in the theoretical episodes. Please go ahead and watch those episodes for the detailed description and the construction. Now here in the practical episode, we will construct the PWL waveform by giving the values and directly using the circuit, as this is an application episode. So here I'll give 0, then I'll give 0, and here I'll give 10 nanosecond, here I'll give 10 volt, and here I'll click 2 millisecond and I'll give 10 volt. So the PWL is constructed here. I'll click OK so that the PWL comes here. Now the PWL line is getting touched here in the inductance. So I'll hit M from the keyboard for the move icon. I'll select it. I'll move it here so that the visually the things looks good. I'll right click to vanish it. Now I'll configure the resistance. This will be 1K. I'll click OK. The L1 that will be 10. capacitance will be 1 micro. This resistor will be 8K. I'll click OK. I'll click save here. So now all the components have received their values. That means all the placeholders have received their values and the input waveform is also defined. Now we have to define the transient analysis. For that I'll go to the Spice directive and I'll type .TRAN. I'll click OK. I'll place it here. Then I'll right click on TRAN to bring the transient configuration window. So here I'll give 1 milli, then I'll give 0, and then I'll give 5 micro. So the details of a transient analysis and its components have already been discussed in the theoretical episodes. I'll not go in the detail here. I'll just do the application. This is because this is a application oriented episode. So here you can see the transient spice command is getting constructed, and this I'll click OK, and it is getting updated here. I'll click save the file. Now I'll hit the run button to simulate the circuit for the transient response, that is the time domain response. I'll click here. And now the simulation has done. I'll go and do 2 checkings. One is go to the spice output log, and having a close look, I cannot find any error or warnings here, and I'll click close it. And next thing, we'll go to the view and then spice netlist. See the spice netlist construction. Here you can see our PWL source is there. Here the resistance is there. Okay. Here the inductance, here the capacitance, and here is another resistance, and here is the transient analysis. So the entire circuit looks good in terms of the spice netlisting also. I'll click and close this circuit. Now I will do click here, hold and drag. So you can see the first one has come. There is the input voltage. I'll hit B from the keyboard, and then I'll click, hold and drag for this particular resistance. So for the resistance this has come. I'll hit B from the keyboard, and then I'll click, hold and drag. You can see the third response. Now if I do the same thing here, if I go ahead and hit B, make a room, and I go here for across the capacitor, I'll click, hold and drag and release. Same thing is coming because the same node. And just for your satisfaction, I'm doing this thing for the same for this resistor. So you can see that all these 3 are in parallel. So one particular voltage node is showing for all of them. I'll hit delete from the keyboard and I'll cut down this thing. Okay, so now the picture is pretty clear. I'll right click to vanish it. Now let me bring my marker pen on. So here this is the input PWL format, and you can see from 0 it goes up to 10 volts and it stays there. And through this resistor you can see the voltage decays, and in this parallel circuit, right, the voltage is going up. Okay, with time, right, the voltage is getting stored here. Okay, and through this resistor the voltage is getting decayed. It's a simple KVL, right? So we consider this as a single unit, right? This voltage is decaying, and that voltage, how much it is decaying, it is getting stored here. Now I will clear the markings here. The transient analysis, that is with the time, that is the time domain, because here you can see in the x-axis it is time. So it is a time domain analysis, and that analysis is done. I'll click and close this, and I'll enlarge the circuit here. Now we are done with the transient, that is time domain analysis. Now we will move to the AC response, that is the frequency domain analysis. For that, the circuit will remain same. However, the input voltage source will change. I'll right click here to change it, and here I'll click done, and then I'll apply a 1 volt small signal AC. And we are not mentioning here any frequency because we will be doing the frequency sweep, that is the frequency variation, through the AC analysis command. I'll click OK. Now the voltage is changed here. Okay, and now I have to comment the transient. So for that I'll right click here, go to cancel and edit text directly, and here I'll select comment. I'll click OK. Now to add the AC analysis, I'll have to go here and type .AC. I'll click OK, and I'll place it here. I'll right click on it to bring on the AC dialog box, AC analysis dialog box, and from there I'll click the decade. Number of points per decade is 10. Then start frequency is 10 Hertz, and the stop frequency is 10 kilo pulse. So here if you look, the AC analysis statement has got constructed and we have given all the values. In the theoretical episodes I have already explained these things. I'll not go in detail. It is an application oriented episode and here we'll go for the applications and the results of a circuit. I'll click OK and here you can see the AC statement, it has come. I'll go and save the file. I'll click the fit to screen and then I will run the circuit for the simulation. The simulation has run. I'll go view and go to the SPICE output log, and by looking closely I don't find any error or warnings here. So I'll click and close it. We already have checked the SPICE netlist, so I'll not go in that direction, but I would like to show you one thing. If I go and SPICE netlist, you can see here the transient is commented by a star. Like the first line of a SPICE circuit is always a comment. You cannot write here. Similarly, it is a comment by star and the AC analysis is active. Okay. So I'll click and close it. Our simulation is done. Now I'll click here, hold, drag and release. So this is our voltage wave. Now I hit B from the keyboard, make the room, and I'll click, hold, drag and release. Now again I'll hit B from the keyboard. As these two nodes are same, right? I'll take only one voltage moving here. I'll click hold, drag and release. Let me bring on my marker pen. Here you can see the voltage amplitude remains same. However, the frequency is varied from 10 Hz to 10 kHz. Here in the x-axis the frequency is changing. So here we are operating on the frequency domain and we are observing the LCR parallel circuit frequency response. So here you can see with the increasing frequency, first this voltage amplitude drops and then it goes up for the resistance. And here you can see in the dotted it is the phase. Now for this parallel combination of the LCR, you can see first it goes light up, then it slowly goes down. Okay, so as we keep on increasing the frequency, the voltage in this particular block will decay and the voltage in this particular block will be getting high. So this is a very simple frequency domain analysis of this particular circuit of LCR, and it's in the parallel combination, and we are using the parallel second combination. In the previous episode we have used the first parallel combination, and here we are using the second parallel combination, and both we have analyzed today is the transient analysis, which is the time domain analysis of the LCR circuit, and the AC analysis, that the AC response, and that is the frequency domain analysis where we sweep the frequency through the .AC command. Now both the time domain and the frequency domain response of the same circuit we have seen in today's episode, and that's all. One thing you can do, you can go ahead and change the values of this components to see what do you observe in the transient domain response as well as the frequency domain response. You can do one small change at a time and then again you can run the simulation to observe the change. This will help you to handle a circuit practically when you are changing a component, and for that it is very cost effective because you don't have to use any physical components. Here you can simulate and observe the change. Here we are done. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.